The modern enterprise security industry is built on a single, universally accepted premise that a cyber attack always leaves a physical trace. We have constructed a multi-billion-dollar defense apparatus around our networks: endpoint detection and response, network detection and response, and sophisticated behavioral AI models. All of these tools operate on a shared logic. They assume that to deny access to your data, an attacker must physically transform it. They scan for specific digital markers: a spike in high-entropy disk writes, bulk renaming of file extensions, the telltale input and output patterns of mass encryption. But threat actors optimize for the path of least resistance, sidestepping established tripwires entirely. The core objective of ransomware is leverage. Attackers achieve that leverage through availability denial. Data destruction is simply one mechanism to get there. This raises a critical problem for the Security Operations Center. What happens to the dashboard if an adversary can sever access to the organization's files without triggering a single write operation? A newly released attack technique has accomplished exactly this. It creates a total zero-write operational blackout. The write action fallacy, the belief that damage requires a physical scar on the disk, leaves the modern security stack blind to an entire class of availability attacks. In May 2026, security researcher Dvash published a proof-of-concept tool called GhostLock. Looking at this benchmark timeline, we can see the speed of the lock acquisition compared to the heavy overhead of traditional encryption. In under 3 minutes, GhostLock incapacitated nearly 500,000 files. Executing this requires no administrative privileges. A standard user account with basic read access is sufficient. For the victim organization, the symptoms manifest instantly. Enterprise resource planning systems crash. Document management platforms freeze. Shared workflow pipelines stall. An incident response team is quickly mobilized. They immediately search their telemetry for expected indicators: tripped canary files, massive encryption routines, or altered extensions. They find nothing. The EDR agent stays quiet. The storage disk remains untouched. Zero alerts are generated anywhere in the security stack. GhostLock achieves the leverage of ransomware while remaining invisible to the primary telemetry modern security teams use to identify a breach. GhostLock utilizes no zero-day vulnerabilities, no CVEs, and no complex exploit chains. It works by abusing the standard rules of the operating system. The core mechanism is a documented, legitimate Windows application programming interface called create_file_w. This schematic illustrates the Windows I/O manager processing a file open request. Notice the DW share mode parameter passing from user mode into the kernel's share access structure. When DW share mode is set to 0, the kernel grants an exclusive deny share handle, preventing all network clients from opening the file. Any other process attempting to read, write, or delete that file is instantly hit with a specific error code: status sharing violation. This check is enforced directly in memory by the NTFS file system driver. It is mandatory, and it cannot be bypassed from user mode. This exact lock behavior prevents two people from overwriting each other's edits. Programs like Microsoft Office have relied on this intended mechanic for 30 years. Because it is a load-bearing operating system feature, Microsoft cannot patch it. Restricting this API call would immediately break the file integrity ecosystem for millions of applications. GhostLock takes the operating system's own rules for data integrity and weaponizes them against the organization. Holding a single file hostage is an annoyance. To be effective for extortion, the attack has to scale across the entire network. GhostLock achieves scale using a 32-thread work-stealing scanner. It maps the server and fires thousands of simultaneous file open requests across the server message protocol. It also features an exponential backoff capability. If a file is currently in use, the script waits and retries until the exact millisecond the file is closed, capturing the lock instantly. A second version of the tool escalates the attack further by targeting entire directories using a parameter called file flag backup semantics. By applying the exclusive handle to a top-level directory object, the attacker creates an instant namespace blackout with a single API call. Enterprise backup agents fail. Users cannot list directories. Discoverability is instantly destroyed. By fusing a legitimate API call with industrial-scale scanning, GhostLock transforms a basic file integrity feature into a tool for systematic, enterprise-wide lockout. This degree of disruption raises a critical question: why does a sophisticated, layered security stack remain completely blind to it? This matrix compares traditional ransomware against GhostLock. Ransomware triggers honeypots. GhostLock uses read-only access, remaining undetected. Ransomware spikes disk writes. GhostLock produces zero writes. EDR sees GhostLock as a legitimate search indexer, and network detection only observes valid SMB requests, bypassing all alarms. This leaves incident responders chasing a phantom. They hunt for encrypted files and malicious payloads that do not exist. Even if the attacker's endpoint is killed, GhostLock can instantly reconnect from another machine and relock the network using its serialized discovery cache. Defending against GhostLock using a traditional stack is effectively impossible because the tools are engineered to look for a crime that isn't being committed. To handle this threat, incident responders must strip away the hype and focus on its strict technical limits. GhostLock is not destructive. It is a persistent denial-of-service attack. The underlying data on the storage array is never altered, exfiltrated, or encrypted. Because the data is untouched, recovery is not a restoration problem. It is strictly a session termination problem. Standard playbooks often start by revoking the compromised user's Active Directory credential. For GhostLock, this is the wrong first step. An already authenticated SMB session will persist and hold its exclusive file locks for up to 60 minutes after the directory credential has been killed. To halt the disruption, the attack must be forcibly terminated at the storage layer by killing the specific SMB session directly on the NAS. Neutralizing the threat requires security teams to put down their endpoint-centric playbooks and directly engage with the network storage infrastructure. There is exactly one place in the enterprise IT stack where GhostLock leaves a definitive footprint: the NAS Management Session Table. In this dashboard visualization, the discrepancy is obvious. A legitimate application might hold 12 exclusive handles. GhostLock simultaneously holds tens of thousands per session. Currently, this handle count metric sits on the storage administrator's dashboard. It is almost never ingested into the central security information and event management system. Defending against this requires bridging the gap between teams, ingesting these per-session handle counts directly into the security alerting pipeline. Network monitors can be tuned to the same logic, triggering on high volumes of SMB create requests that never result in a single write operation. As long as the security industry remains obsessed with the right action fallacy, adversaries will exploit the chasm between how data is stored and how it is actually defended.